Hi, good morning and welcome to the ZP Developer Zone. So every Thursday at 8 a.m. London time, we like to do a free webinar for members of our ZP Developer Zone, and we also like to answer essentially technical questions. So I always say this, but let's really try and jump straight into it. We've got a lot to cover in the next few hours, not hours, the next few minutes. All right, so let me just jump into it. First of all, thank you. There's been a lot of increase in membership on the ZP Academy recently, and that's because we have put a course up on the ZP Academy about screen-printed electrodes, and I think that has raised the interest. Now, it should be said that that's a paid course, but there are a couple of free courses on there. So if you're interested in electrochemistry in general, there's a free course, and there's one specifically on biosensors as well. So there's the Academy. We have these webinars every Thursday at 8 a.m. London time. We do essentially a webinar for the members of our ZP Developer Zone. We have collaborations. We have a ZP Developer Zone member coming in this summer. We might actually have two coming in this summer, but we definitely have one. In fact, we definitely have two when I think about it. So looks like a guy coming in from Turkey and a guy coming in from Malaysia, so that'd be great. And then we have our ZP Developer Zone website. And then we have workshops, and we have a workshop being hosted with Elsevier, the publishers, and that'll be in a conference in Spain. So we are definitely doing that. Now, in terms of questions, we use this webinar every Thursday at 8 a.m. London time to answer questions. So question number one, somebody wants to order a ecFLEX, and it comes in two types: OCP, which stands for open circuit potential, and amperometric, and we will discuss the difference between those two things. We've had another inquiry about gold screen printed electrodes. I'm going to talk about screen printed electrodes in general and touch upon the fact that gold prices are really kind of escalating and spiraling at the moment. I'm really thinking this is not something that's going to change. We had an inquiry about phosphate sensors. We'll talk about the hardware and the electronics for that. And then finally, we had a nice one here, the shape of electrodes. There's a lot of different screen printed electrode shapes out on the market. Is it really necessary to have all these shapes? And we'll discuss that as well. So somebody like an ecFLEX reader, they have what they call CA, chronoamperometry, and open circuit potential. What's the difference between the two measurements? So this is our ecFLEX hybrid. This is the circuit itself. This is the sensors. And you can either put into there what I would call ion selective electrodes. Under ion selective electrodes, I would talk about phosphate, sodium, potassium, pH. Now at ZP we are tending to walk away from this board these days, and there'll be another board that we're starting to recommend. But if you're interested in wearable sensors, then this is probably the best off-the-shelf wearable sensor board that we have. And as I say, it comes in two modes: OCP, and open circuit potential is used with our ion selective electrodes, phosphate, potassium, sodium, nitrate, pH, calcium, things that are generally ions. So I just listed out a bunch of ions there. Now there's another mode which is also amperometry, and that's for measuring mostly the the enzyme-based sensors. So I think about the enzyme-based sensors, that would be glucose and lactate, maybe cortisol. I measured the alcohol already, probably. The ketone sensor, sensors that have an enzyme at the base of them. So we often use amperometry for enzymes and open circuit potential for ions. So there are lots of videos on the ZP website, and we discussed this. But the sort of four main techniques that we tend to use at Zimmer Peacock are voltammetry. You change the voltage, you measure the current. Amperometry, you hold the voltage and just measure the current. Open circuit potential, you just measure the voltage. And then the last one that we use quite a lot of is impedance spectroscopy. And in fact, if anyone's making an immunosensor, I would recommend impedance spectroscopy. I just want to say hi to Hitcham. Nice to see you this morning, Hitcham. Thank you for coming along. So the questioner was asking, I want to buy an ecFLEX. It seems to have an OCP mode and an amperometry mode. The OCP mode, the open circuit potential, is used with these ion selective electrodes. So you'll also see us use the word potentiometric, which just means the measurement of voltage or measurement of potential. You're very familiar with potentiometric sensors. These are the kind of pH sensors that you see in the lab, so you are familiar with them. Now at Zimmer and Peacock, we have reduced these bulky pH potentiometric sensors down to things that are quite small. So there is a movement now, down to solid state. The way these potentiometric sensors work, and this is true for things like phosphate, pH, sodium, potassium, chloride, calcium, they all sort of follow essentially what's called the Nernst equation, which kind of says you have to measure the voltage, and that's why we have an open circuit potential mode on that ecFLEX, and that voltage is proportional to the log of the concentration. So if you ever wonder what the P and pH means, it means minus log to the base 10. So the voltage is proportional to the log of the analyte of interest. And so what we're doing is this, that there's essentially two electrodes that we're using. One's specific, it's called an ionophore, and the other one's the reference. We measure the voltage between these two, and we tend to, we don't make these large glass stainless steel constructions. No, we try to use much lower cost, much more robust ways of developing these sensors. So we have a working electrode, which has an ionophore on it, and we have a let's say counter electrode, which has the reference electrode on it, and the ecFLEX is measuring the voltage between it. In a minute, we'll actually talk about a different type of board for use with a phosphate sensor, but they both do the same. They're measuring the voltage between two electrodes. Now in amperometry, so in open circuit potential, I use the word potentiometry, which just means measure voltage. I used to use the term ion selective electrode. In those open circuit potential measurements, we were just measuring the voltage. In amperometry, we're applying the voltage, and it often is something like 650 millivolts versus the reference, and we just measure the voltage. We apply the voltage and we just measure the current. The kind of sensors that this mode is often used with is something like a glucose sensor, where you might have an electrode, a mediator, an enzyme layer on it, which for example could be glucose oxidase, and a barrier layer to somewhat protect the enzyme and not necessarily let all of the analyte get to the enzyme sensing layer. So just turning that on its head. So an amperometric mode is often used if you're going to want to detect glucose. Then the barrier layer is to sort of essentially half block the glucose. Some of the glucose goes through. Within that enzyme layer, the glucose is reacting with glucose oxidase. We get a reduced form of glucose oxidase, and the reduced form of glucose oxidase reacts with oxygen to give us hydrogen peroxide. And this is where the sort of amperometry starts to kick in, because that is electrochemically active. If we're doing what's called a generation 2 sensor, then we'll have a mediator in the system, which mediates the flow of electrons from hydrogen peroxide down to the electrode. Now for that mediation to take place, we need to apply a voltage. And in a generation 1 sensor, we might not use the mediator, so we have to apply a different voltage, but it's a simpler construction. So we have generation 1 and we have generation 2 sensors. So the difference between amperometry and open circuit potential really depends on what you're trying to measure. If you're using one of our enzyme sensors for small molecules, then they're often amperometric. If you're using one of our ion sensors, then you would run really what's in an open circuit potential mode. You would measure that using potentiometry, and the style of sensor you're using is often ion selective electrodes. Sorry, that was a long answer for a short question, but we like to be thorough. Now this question here is somebody's interested in one of our gold screen printed electrodes. I used to make the statement, it didn't matter if you used carbon, gold or platinum, but that is, I like things, there's no certainty in life, and the gold and platinum prices obviously are spiraling. I really don't think this is going to change. I think this is the way we're going. So let's talk about gold electrodes. First of all, let's talk about what's wrong with gold screen printed electrodes. I mean, this is true not only for gold, but carbon and platinum and all of them. Most screen printed electrodes on the market are too big, and what I mean by that is their dimensions mean that the volume, the manufacturing of them means that you can't pack enough of these electrodes into the manufacturing process to make them that economically viable. So the smaller something is, then generally the higher density of manufacturing you can make, and therefore you can make more of them within a certain unit of time, and therefore they're lower cost. So most screen printed electrodes on the market are actually too big. They're nice for R&D, and people get very fixed on them, but if you really do the calculations when you want to go to volume, they don't make any sense. They're too expensive. The other thing about screen printed electrodes is they're really made in too small a volume. If you really talk to people who've been doing R&D for years, they won't complain about the ZP sensors or the ZP screen printed electrodes, but they will complain about others, and they say that the quality's not good. What it is they're actually made in such small volumes, they're essentially almost not manufactured. They're made in what's called a batch, and then they may not make that sensor for months again. They make a batch, they put them on the shelf, they sell them. When they run out, they make more. Now, when you manufacture like that, that's not really a continuous manufacturing process. That's batch manufacturing. So they're almost not relearning, but the setup every time is slightly different, and the quality is changing a little bit every time. So most screen printed electrodes for the R&D market are made in too small a volume, and most screen printed electrodes are on the R&D market are actually made for R&D, but they don't really have a vision on being screen printed electrodes for being into products. And now at Zimmer & Peacock, we don't make screen printed electrodes for the R&D market. We do sell them to the R&D market, and they look a bit different to everyone else's screen printed electrodes. And it's because we're the most, I would say, commercially orientated of these manufacturers that, we're really thinking about how is this electrode going to play out in a real product? Because everyone's going to come to at some point and say, I want a screen printed electrode. I need high volume and low cost. And that's the vision we've kind of got for our screen printed electrodes. And lastly, gold pricing is spiraling, and I'll cover that point as well. So for Zimmer & Peacock, it's been a little bit of a journey. So when we first started out, this was one of our gold electrodes. It's called the Gold 101 for us. If I was to criticize it today, it's too big. It doesn't play well into microfluidics, and I will touch upon that in a bit. And also, when people like this circular pattern, because the reason they like it is because in an R&D setting, you can get a pipette, you can just drop a solution on there, and it will sort of spread around. Now, we actually came up with a slightly better design, and we do carry this one in. We manufacture more of the better design than we do the original 101. So the 101, it's got a white layer around here, and that's a little hydrophilic. So what tends to happen is things tend to sort of spread out a bit. So we put a hydrophobic barrier here, and that actually helps to sometimes contain the solution. So that one we call the 101B, so because there's a bit of a barrier layer there, and it actually helps to contain the drop. So that was a bit of an improvement. I said it was a bit of a journey here. The electrode that we recommend today is this 303. It's smaller, it's half the price. You look at the rectangular design, you say, what's that all about? And the reason it's got this rectangular design is because we generally imagine that people are going to put these into products, and at some point they might end up in what's called an in vitro diagnostic, which is really just biosensors within microfluidics. And so when you have a layout like our 303, it means that you can have your electrode in a channel, solution can come down the channel, go over the electrodes in a sequence, and as it goes over each electrode, that will really give us a electrical signal, so we can know when the solution has gone between the first electrode and the second electrode, and from the second electrode to the third electrode. There will be a signal associated with that. So it really helps us know that the sensor's been filled, and it really allows us to automatically start the assay. And so I just want to say hi to Aftab, who's come online this morning. Hi, Aftab. And whilst AFTAB's online, I'm just going to say quickly, we'll probably do a dedicated webinar next week about CGM. So if you're particularly interested in continuous glucose monitoring, I think we'll do a dedicated webinar on CGM next week. But the reason that we have these rectangular electrodes and they're laid out the way they are is because we're imagining that eventually these are going to be in a product, there'll be a microfluidic channel, and we want to be able to know when solution is arriving in that channel, and this geometry allows us to do that. Now finally, so most gold electrodes are too big. We've had a bit of a journey on these gold electrodes. We've shrunk them down, we've halved the price, and we have a rectangular design because we imagine they'll be in products eventually. Now I would actually say gold is spiraling out of control, and actually I think that carbon, because you get so many sources of carbon in this world, it's never going to have the same kind of price pressures on it like gold and platinum would. So I'd actually suggest that whenever somebody asks about gold electrodes, I often think they're actually going to make an immunosensor, and you can make an immunosensor using SAM, self-assemble monolayers, and you can also make immunosensors using carbon. So I personally recommend something called the hypervalue carbon electrode. It's super low cost. It's 99 cents. It's basically and that's at low volume. It's a fraction of all the other electrodes. It's super high quality because actually we make it a really high volume, and it looks just like a glucose sensor. So it can essentially tell you that we've taken all the aspects that allow people to make low cost glucose sensors and put it into this screen printed electrode. I just said that if you're making whenever people are asking us about gold electrodes, they're always really asking us about immunosensors. I'm not going to dwell on all of this. Hitcham and AFTAB are online. I've seen us do many webinars on this. If you're going to make an immunosensor, just read this paper. We talk here about how to do the functionalization, and we talk here about how to do the detection. It is in the paper. There are other webinars that we've done many times on this. I'm not going to talk about it today, but if you're using gold electrodes for your immunosensors, truly thinking about using carbon electrodes for, especially that hypervalue carbon electrode for doing an immunosensor. We do it. It works perfectly fine. In other videos, if you come back and ask me, I'll talk about it again, but we actually suggest you use EIS, electrochemical impedance spectroscopy. We do have quite a few of those EIS instruments on our website. I'm talking fast because I feel like I've had a long answer on ecFLEX. I know it's very detailed. Now I've had a little long answer on gold screen printed electrodes, which I ended up saying, actually, if you want to stick on gold, use what's called the 303. I generally say go for carbon. Somebody's interested in phosphate sensing. Now for phosphate sensing, we have what's called we have an OEM board for ion selective electrodes. It's pretty low cost. It's about 250 euros, which, if you're in UK pounds, that might be somewhere like in the £210 region. It works with our phosphate sensor. There's just one, and there's a link here to the phosphate sensor, and there's a link here to the OEM electronics that we're talking about. So that would be the package I would use for phosphate sensing. Now the only thing about it is the phosphate sensor that we have is phosphate has many speciations depending on the pH. So the phosphate that we are sensitive to is this kind of monoprotonated phosphate here, which is the dominant species when you're kind of working from something like pH 7 to around about pH 12. Now I'm not suggesting that this user is anywhere near pH 12. They're probably in the range, approximately I would sort of guess, pH 6 to maybe pH 8. So it gives you a sense that this speciation changes, and this is the one we're sensitive to. The quick answer on this is, as well as measuring phosphate, you also have to measure pH, because then you can back calculate the phosphate concentration from the pH, and we also have a pH sensor as well. So I suspect some follow-up questions on this, but the quick answer is we have an OEM solution for ion selective electrodes. We have a phosphate sensor. Phosphate is a little complicated because it changes its speciation depending on pH, so you really need to measure pH as well. And it's kind of nice really, because measuring pH and phosphate, you can calculate, you know what the pH is, which is a nice start, and actually you can calculate more accurately the actual phosphate concentration. Again, there's a lot of information there. I'm not going to be surprised if I get more questions. Now this is a good question. Why have we got all these different shapes of screen printing electrodes? why have we got this? And in the end, I'm just going to say, make a recommendation. So if you look at Zimmer and Peacock, we have the circular one, and I've discussed this one. It's circular, it's easy to pipette onto. People like it in an R&D setting. So, that's one of the first ones we had. Then we put this one on that's got this very thin green layer here, and it basically acts as a barrier layer, and it sometimes helps hold the drop. This one was because some people wanted to use less solution and less sample in functionalizing it, and also there's a belief in electrochemistry that you need a larger counter electrode to your working electrode, and that is it can be a true statement. The proper statement is you need a faster rate of reaction on your counter electrode than your working electrode. So the true statement is you need a faster rate of reaction on the counter electrode versus the working electrode, and one way of achieving that is to have a larger counter electrode. But often we actually use a silver chloride as our counter electrode because it has a fast rate of reaction. The conversion of silver to silver chloride is fast, or the conversion of silver chloride to silver is fast. So the statement that I need a larger counter electrode is actually not true. It's just you need a faster rate of reaction, and you can often achieve it through size, but we achieve it through a cleverness. So we have one size of electrode, another size of electrode, a smaller electrode. Here we have a spiral. We did the spiral because some people are interested in measuring impedance. They think that interdigitated electrodes are a good idea. Interdigitated electrodes are really kind of lines of electrodes that are very close to one another. And so we achieved the same as an interdigitated electrode, but we did it in a spiral format. The quick answer is we found out that actually it doesn't matter what this geometry is. You often get, it really doesn't make a critical difference to a sensing application. You might have a slightly higher current density with some of these designs, but it's not so critical that actually it's not the thing preventing you from a successful experiment. Here we have a very much smaller electrode. Our idea here was that people might want to make wearable or implantable sensors and would want to kind of test out those sensors or those sizes. This one's even smaller. Now this electrode was based like this because earlier on I was talking about an in vitro diagnostic where a sample might come in and onto a sensor due to capillaries or microfluidics, and so we imagined that the sample might come in from the side, and so we had a sensor where the sample come into the side and sequentially cover the electrodes. And here the next one we had the idea that the sample might come in from the top and sequentially cover the electrodes. So there's a reason for all of this, and when you look at all the screen printed electrodes out there on the market, what it means is that everyone has different geometries and people are sort of choosing these geometries, and so it leads to a very fragmented market. That means that when people buy electrodes, they're disappointed by the quality, and the reason they're disappointed by the quality is because none of these manufacturers are really manufacturing this in high volume, because their product line is so wide, it ends up fragmenting what people are buying. So people are just buying 200 of this, 200 of that, 200 of that, and they're not buying high volume. And if you don't have high volume, you can't have good manufacturing, and you can't have good quality and low cost. So all these designs are fantastic. Really, when it comes down to gold electrodes, for example, I just say use the 303. We manufacture it in high volume. We use it ourselves. It's high quality and it's a fairly good low cost. And I genuinely say to people these days, sorry, but gold is getting expensive. Platinum's getting expensive. Use these hyper value carbon electrodes. They're low cost and they are high quality. AFTAB and Hitcham are sick of me saying this. They're online today. The biggest user of these electrodes is Zimmer and Peacock. So it's we protect the quality for ourselves, and by the way, we make them available on the web store as well. So I've spoken almost continuously for 24 minutes. I have my shirt and jumper on today, so I do have some meetings coming up, and I like to try and be efficient with your time. So let's summarize. The ecFLEX comes in open circuit potential mode and amperometric mode. Open circuit potential mode for ions, phosphate, nitrates, sodium, potassium, chloride, magnesium, pH, etc. And the amperometric mode is for the glucose sensor, for the enzyme sensors, glucose, ketone, lactate. It actually works with oxygen as well. Alcohol is also on there, and so we got a whole list of enzyme-based sensors. Gold screen printed electrodes. 101 is fine. 101B is slightly better. The 303, we make it high volume. We use it a lot. We like it. But generally, there's a paper I've put in this presentation today that says if you're going to use it for immunosensors, come off gold, because I really think the gold price is high. We are in financial uncertainty times. I'm not really sure this is going to get any better, so come on to carbon. Phosphate sensor, I would just start off, get a phosphate sensor, get the OEM board that I suggested, make some measurements, but know that it's pH sensitive, and you probably have to have two boards, one dedicated to pH, one dedicated to phosphate, a pH sensor in the pH board, and a phosphate sensor in the phosphate board. And then you would do a calculation to back calculate. Shape of the electrodes, yeah, there's a lot of shape out there. There's a lot of discussion in the literature about this. Our honest opinion is, yeah, the absolute current and current density can change with shape, but it's not preventing good science, and it's not preventing good products. It's actually just leading to a lot of fragmentation in the market. Each sensor then is made in low volume. The low volume means it ends up being high price or low quality as well. All right, well, I suppose it's enough to say thank you. I appreciate you all attending today. Thank you, Hitcham. I hope to see you very soon. Thank you, FTAB. I will talk to you as always very soon. And if you have any questions, reach out to us at Zimmer & Peacock. As you can see, we tried to answer any questions. If we've forgotten your question today, I do apologize, but we will answer them. And next week, I have a very strong suspicion that we're going to dedicate a big chunk of this to continuous glucose monitoring, because we are getting a lot of inquiries about it. Okay, thank you very much.